Thank you very much. Welcome to the Department of Chemistry, and today's lecture is all about light, and we're going to be looking at ways we can generate light and think that some of the reactions that we can bring about with light. Okay. So first of all, what exactly is light? Well, this isn't going to be a physics lecture, you'll be pleased to hear, so we're just going to treat light as a source of energy. Now we can convert one energy source into another energy source, and this is what we're going to be doing today, and we're going to start off with some chemical light. Now, presumably the first light, the first artificial light that must ever have been formed must have been as man had made fire. As soon as he'd made fire, he could lift up a branch and light his way with this. Okay. Well, this is, of course, just the combustion of the wood. And the wood is made of cellulose, which consists of carbon, hydrogen, and oxygen. But later moved on to more sophisticated fuels, and we have a slightly more sophisticated fuel here in this Roman oil lamp. And actually, the fuel used in this lamp is olive oil, just normal olive oil. Here we have the olive oil, and the lamp is beginning to burn. It'll probably get going slightly better during the course of the lecture. So there's quite a bit of light being given out from this. And also we'll light the candle, if we can get this going as well. There we go, lovely. Both of these are fats that are burning here. Okay? The olive oil is a type of fat. It doesn't sound quite so nice when we call it fat, but it is a fat. And indeed the candle wax is also a type of fat. What is a fat? Well, we've got part of the structure of a fat at the top here. We thought we'd try and make a whole one, but we didn't have enough hydrogen atoms to make one, unfortunately, because it's rather large. There are actually 3 of these units in a typical fat. It's a long chain consisting of the black atoms, well, these are carbon atoms, the white atoms are the hydrogen, and in this, well, there are just a couple, 2 red atoms, these are the oxygen atoms here. But there would be 3 of these units linked together with another short chain, which make up a typical fat. And it's these that are the burning here. The carbons burn in the oxygen to form carbon dioxide. We have a carbon dioxide molecule up there. And the hydrogens, if there's enough oxygen, can form water. And there's some water molecules over there. Okay, so, well, perhaps we can just have a look on our periodic table to see where these elements are. And perhaps those with laser pointers can help me out here, please. Can you point to carbon, please? So where's the carbon? Oh, not bad. Yes, some of you have found carbon, I think. Yes. And what about hydrogen? Can you find hydrogen, please? Yes. I don't know what this one's doing down here on promethium. Anyway, yes, so there's hydrogen. And of course, these are burning by reacting with the oxygen in the air. And where's oxygen? This way. Very good. Yes, some of you are nearly there. Very good. Okay. These are the fuels we're seeing here, the fats, carbon, hydrogen, and maybe a little bit of oxygen. Well, some fuels contain just carbon and hydrogen only. So if I turn the gas on here from my Bunsen burner, this fuel is a hydrocarbon and consists only of carbon and hydrogen. And we see that this gives out a lot of light as well. Very nice. Actually, all of these have something in common. This one is clearly burning a gas. It's the gas burning with the oxygen from the air. But these two are also gases. Okay? So the olive oil, first of all, has to vaporize and turn into gas before it can burn. Even the candle here, first of all, it liquefies and there's some molten candle wax on the top, and then that has to vaporize to form a gas, and that gas is the thing that's burning. Well, can we burn just any old gas then? Actually, no, we can't. Here we have some hydrogen. Hydrogen burns very easily, so this is hydrogen and oxygen burning. It's a very, very hot flame, and we'll come back to this later. But there's very little light coming out from this. So there's a lot of energy being given out, but it's mainly in the form of heat energy, not very much light. So how come our gases that are burning in the center of the stage there give out quite so much light? Well, one of the important things we need in the gas is the carbon. And what we're actually seeing here are little particles of carbon, soot, that have been heated up, and so they're glowing, and it's that glowing that we see here. So the fuel needs to contain some carbon in order for us to see this. And I can show this, actually, with a piece of white card here. So if I just hold this over my Roman lamp, I should be able to trace out, so that's the soot given out from this lamp, the black soot there, and this is carbon that's formed due to the incomplete combustion of the fuel with the oxygen. But it's these particles of carbon that give out all the light that we see. Now we're going to burn some other fuels here, some other hydrocarbons. And first of all, we're going to start with a gas very similar to the methane in the Bunsen burner here. This gas is called ethane. And this consists of 2 carbons and 6 hydrogens. Now, let's watch very closely the flame that we see here. Are you ready? It's rather nice, but not very much soot. Not very much soot was given out there. Now we're going to try slightly different gas. The first one was ethane, and I said there's 2 carbons and 6 hydrogens, and there's some ethanes flying around over there. The next ones we're going to use are, this is ethene, and this consists of 2 carbons again, but only 4 hydrogens. Are you ready? Now see if you can compare the flame to the first one. Okay, it seems to be a little bit more sooty there. There's a little bit more black carbon being given out. Now the final gas we're going to use here is ethyne, and this has 2 carbons again, but only 2 hydrogens. Now look very carefully at this flame. If we have the lights up for this one, please. Right, are you ready? Look at the soot. So in this one, there's very little hydrogen compared to the amount of carbon in this one, and so now the whole lecture theatre is filled with this little black snow that's going to gradually come back down on top of us. Well, ethyne used to be used in portable lamps. So this was before the days of batteries and so on. What did you use on your bike? Well, you'd used to have a little lamp like this. This is an acetylene lamp here. And the reaction to generate the gas, well, we've got water dropping onto something called calcium carbide. So in the slide at the back here, we see the lamp, and this here is the calcium carbide. Adding water to this gives the gas, ethyne. So this is the very fine jet here is getting a chance to mix with the air around here now. We haven't got a big load of the gas there, just a very fine jet. We get a very white coloured flame there. So we've still got the particles of soot, and they're still being heated up by the energy given out of the reaction. The soot is still coming down. We're still getting black snow coming down from the ceiling. But we can get our ethyne or acetylene to burn completely if we mix it with sufficient oxygen. And this is what we're going to show here now. This is the equation that we want to do. We want to burn our ethyne completely. So we've got ethyne reacting with oxygen, and if we burn it completely in oxygen, we form carbon dioxide and water. Now, this is a little bit more violent, though, if we do this. So we've just put in the bin here a small flask containing the ethyne and the oxygen mixed up in just the right ratios. Now, if this works, it might go with a bit of a bang. So I'm going to have to ask you to put your fingers in your ears, just to protect your ears, especially those in the front row. Okay, we'll count down from 3. Okay, are we ready? 3, 2, 1. There we go. And that's what's left of our bottle there. Okay, so perhaps I'd like to pass that round. Oops. So far then, we've only managed to get our light out of the fuels containing carbon, hydrogen, and maybe a little bit of oxygen only. Okay? Well, many other elements are involved in producing light, and we're going to look at some of these in the course of the lecture. In fact, one element was named after its ability to produce light. Okay? This element was discovered in the late 1600s. Okay? It's been known for a very long time, over 300 years. This element is called, does anyone know what it is? Phosphorus. Oh, somebody's very good there, yes. Phosphorus. So phosphorus is named from the Greek, meaning the light giver or light bringer. Well, we better find it in the periodic table. Time to test your chemistry again, those with lasers. So can you find, oh, very good, yes. So it's P for phosphorus. That's it, there seems to be a gathering of laser pointers just around the phosphorus, very good. Well, why was this discovered quite so early on? Say this is a very, very reactive element. In fact, so reactive that it spontaneously ignites in air. Why was this discovered so early? Well, one of the reasons is because of the rather gross method used to make it. Now, I have a description here, and it was actually initially made from urine, okay, or wee, all right? So here's a description from the 17th century. It says, take a good quantity of urine, newly made by those who commonly drink beer. Apparently that works better. Okay, evaporate the humidity by a slow fire in an earthen vessel until it comes to the consistence of an extract of thick honey. So this is really horrible, gooey stuff now. Okay, then you put all the matter together in an earthen pot, set it in a cellar, and cover it and leave it there for 3 to 4 months, that it may ferment and corrupt. So this is really horrible stuff now. Well, after that, you add some sand, heat it up, and distill out the phosphorus. And the phosphorus needs to be collected under water, and this is because it is so reactive. I say there are 2 reasons why it was discovered quite so early on. One is the really gross method for making it, and the second one is because, well, once you had made it, you really couldn't miss it. And this is because of this fantastic light that it gives out. Well, here we are. This is a rather nice painting with an alchemist in front of phosphorus here. He's just observed this distilling over, and he thought, what on earth is this? This has a rather catchy title, this picture, the painting here. It was painted by Joseph Wright of Derby, and the title of this painting is The Alchemist in Search of the Philosopher's Stone Discovers Phosphorus and Prays for the Successful Conclusion of His Operation, as was the custom of the ancient chemical astrologers. So not exactly very snappy, but nonetheless it tells you what's going on here. Okay, here now is the description of phosphorus from 1698. And this was in a book called A Course of Chemistry by Nicholas Lemery. And he says, after some experiments made one day at my house upon the phosphorus, a little piece of it being left negligently upon the table in my chamber, the maid, making the bed, took it up in the bedclothes she had put on the table, not seeing the little piece. The person who lay afterwards in the bed, waking at night, and I like this bit, perhaps through the more than ordinary heat he felt, perceived that the coverlid was on fire. It seems that the phosphorus, being heated with the body of him that lay in the bed, had set fire to the coverlid, and before he had perceived it, had burnt a great hole in it. Well, I thought we ought to demonstrate this to just show you how reactive phosphorus really is. So, okay, I'm going to get some phosphorus in a second. It's really rather unpleasant stuff, so I need to put on my gloves here. And Mark is going to bring some warm sand. We've had some sand warming up in just in the corner there. Let's get the phosphorus out. So I'm just picking up a tiny little piece. So it's on the sand, and it's already caught fire. Oh, there we are. Look at that. So look at this. The light that we see here now is the reaction between this very reactive phosphorus burning with the oxygen that's in the air inside this flask, and it's making phosphorus oxide. This is a chemical reaction, but this chemical reaction is giving out light as well as heat. Okay. So here's the chemical equation for this reaction. Phosphorus plus oxygen gives phosphorus oxide. This is the smoke that we can see in here, the white smoke. This is coming over the tube and being absorbed in the flask here. Okay, so that was an element, phosphorus, the light bringer. We're going to go back now to our hydrogen. And if you remember, the hydrogen didn't really give out very much light when we tried to burn that, but we can get some light out of this, if we're rather clever, by heating up something that gives out some light. So this is what we're going to try now. We've got the hydrogen and oxygen light here, and we're going to heat up, well, this is a stick of chalk, exactly the same sort of thing that your teacher would use. So we're heating it up. If we have the lights down, please. Look at this brilliant white light. Okay. So there's a chemical reaction going on. Well, the chalk is calcium carbonate, And under the heat here, this is forming calcium oxide. And it's actually the calcium oxide that is glowing. We have a lump of calcium oxide on the top here, and just heating that up, we can get the same light out. Now, calcium oxide is also called lime. Now, this light source was used in early theatres. So when they wanted a spotlight on somebody, well, how did they get their bright light? Well, there wasn't any batteries and light bulbs at the time, so they used this chemical light from the lime, and hence it was called lime light. Okay, we still have this expression now, in the limelight, and this is how it was generated. Well, how exactly did they do it? Well, this is the sort of apparatus that they used. Similar to ours, there's the taps here with the hydrogen and the oxygen coming in. We need hydrogen and oxygen because we need a really, really hot flame in order to excite the calcium oxide sufficiently. Okay, so the gases come in here and then come out of a little jet here and play on the calcium oxide or the lime. Okay. How did they get their hydrogen and oxygen? Well, they used to have big balloons, big bladders here filled up with the gases. And then when they needed to turn up the spotlights, somebody sat on the balloons to try and get the gases to come out more forcefully onto the lime. But there is, of course, a bit of a problem with this, okay, with the bags of hydrogen. And that is, of course, that hydrogen is also flammable. Oh. And it's blown my candle out. And actually, there was an accident in the Drury Lane Theatre in London with one of these hydrogen balloons blowing up. And so after that, well, they had to rethink their method of lighting the theatres, and the limelight was abandoned. Okay. Well, it wasn't until over 50 years later that something else was discovered that also gave out this light, but without such high temperatures. This was actually discovered accidentally. So a chemist was heating up a mixture of solutions and it boiled over onto his gauze, okay, and it started to glow in the Bunsen flame. And we use this nowadays in light mantles here. So this is a camping light. We have a source of gas here, butane. This burns and it plays on the mantle at the top of the lamp. So this is the white element that we see at the top there. And this is composed of some rather rare elements. We have oxides of magnesium, lanthanum, yttrium, and zirconium. Okay, well, let's see if we can get one of these to work. I've got a mantle here. So here is the mantle from one of these lamps. And just with my Bunsen flame, well, first of all, let's just try and heat up the gauze. So my Bunsen burner can get things red hot. So a metal or something like this glows, but it only glows red hot. There's not really very much light coming out of that. But these oxides, these particular compounds, when heated, give out a really, really brilliant white light here. So this is much better at converting the heat energy into light. But only certain compounds will do this. So let's see if we can find these on our periodic table then. So where are we? We have yttrium. We find yttrium. Very good. Yttrium's the Y. Zirconium. That's quite easy. That's the one next to it. Lanthanum. Very good. Down here. After a while, it was found there was another element that worked even better than these ones, and this was used for quite a long time. And this element was thorium. Can you perhaps find thorium for me, please? That's down the bottom there. Very good. So there's thorium. But thorium is just 2 spaces away in the periodic table from uranium. Okay, here is uranium. Okay, so thorium, like uranium, is also slightly radioactive. Well, I have here an original mantle, one of the early types. It's still in its little plastic bag. We bought this fairly recently. The one that we have in the lamp is actually a modern one, made of these other elements, yttrium, zirconium, and so on. But this one does, in fact, contain thorium. And we should be able to see that this is radioactive. Now, I need to just get down here so you can hear the clicks from the Geiger counter. So even though it's still in its packet here, you can hear that it is rather radioactive. So I'll put that one back in my radiation-proof box, I think. There we are. So we no longer use thorium, even though it's actually the best at converting heat into light, better than any other oxide. Okay? Thorium oxide actually has the highest melting point of all of the oxides and is very good for converting heat to light, but I say it's abandoned now because it's radioactive. One of the reasons that people wanted a good light source was in photography, of course. I mean, so nowadays we have our cameras and they have a built-in flash, it's all rather nice, but what did they use before we had these flash guns and the flash cameras? Well, this is one of the apparatus that was tried for a while. Inside the tube here, there's a gas called nitric oxide. This is a colourless gas, but when we take the top off of this, you may well see a brown gas coming out, and this is due to the reaction with the nitric oxide reacting with the oxygen in the air, forming a brown gas called nitrogen dioxide. Well, I'm going to add some carbon disulfide to this. Carbon disulfide is a little like carbon dioxide, but instead of the oxygen atoms, the two red atoms that we see in the carbon dioxide molecule up there, we have sulfur instead, carbon disulfide. So we're mixing these two reagents together, and in a moment we're going to apply a light to the top, and you should see some light forming. Okay, thank you. Just in case you missed that one, we'll try a slightly bigger one. Okay, so we're mixing the two together. The nitric oxide, NO, and the carbon disulfide. If we have the lights down, please. Thank you. Remember, the carbon disulfide contains sulfur, and the yellow colour that we see here is due to the sulfur that's been formed in this reaction. Okay, well that seems rather inconvenient. We wouldn't really want to take one of those along every time we wanted to take a picture of somebody. So obviously people were looking for other ways to light up for their photographs. Now, one way we can do this is by burning certain metals. And a very good metal to burn here is magnesium. I have a little strip of the metal magnesium here. Look at the light that this gives out. So a brilliant white light as this combines with the oxygen from the air to form magnesium oxide. So this is actually an early little magnesium ribbon dispenser as used in photography. So we'd have the magnesium wound up in here, and we'd gradually feed out a little bit of the ribbon that we would light as we needed some light. Here's the chemical equation here. We have magnesium combining with oxygen to give magnesium oxide. Well, that was all very good for a long, bright light. What if we wanted a very quick flash of light? Well, you may have seen in early films when the photographers would be carrying one of these flash lamps here. Okay, and there's a little ridge here, and on the ridge we have some magnesium powder and another metal, aluminium powder. And this is going to react in a moment, but not with the oxygen from the air, but with oxygen from another chemical called sodium perchlorate. Okay, so we're going to put an electric current across here, which should trigger this reaction. And this is exactly the same sort of thing that early photographers used to do. They used to hold this themselves. Well, I'm not going to hold it. I'm going to step back here. Okay, so we'll have a countdown again. 3, 2, 1. There we are. There's a rather nice smoke ring just forming at the top. And the smoke that we get that's settled to the top of the lecture theatre there, well, this is the same sort of thing that you'd have if you have indigestion. It's magnesium oxide. You may have heard of milk of magnesia that can sometimes settle your stomach if you're feeling a bit ill. Well, this is the smoke that you see at the top of the theatre now. You may well have seen other metals combining with oxygen. In fact, on November the 5th, you would probably be noticing these. Here we have a sparkler, and this is, of course, burning iron. These little sparkles that we see from the sparkler are due to iron filings that are heated so hot they glow. Well, perhaps we ought to find these elements that we've been looking at on our periodic table then. So here we are. So in the flash we had magnesium. There we are, magnesium, very good. We also had aluminium. Yes, over here, very good. Okay, and the sparklers contained iron, and the symbol for iron is Fe, ferrum. Very good. So, this gives us a clue actually as to the way the modern lamps actually work. If we heat up some metal, it glows, and maybe that could be used as the light source. Well, actually just passing an electric current through some iron wool, we can indeed get some light. So if we just have the lights down, that's great. So we can see here, just applying a battery to this iron wool, it's causing some of this iron to glow bright, just like the sparklers. Well, could we make a light bulb from the iron? Well, no, we couldn't. We couldn't because it's just too reactive. It combines with the oxygen far too readily. So they looked at some other elements instead. Now, one of them that they tried was platinum. Can we find platinum, please? There's, well, somewhere. Yes, that's it. It's centering there. Platinum. There's platinum. But the problem with platinum, it worked very well, but it's far too expensive. In fact, some of you may well have jewellery made of platinum. Instead of platinum, another element was tried, and this element is tungsten. Where's tungsten, please? Some of you are all over the place. But yes, some of you are centering around here. This is a trick one, of course. Tungsten, the symbol for tungsten is W, named after wolfram, a different name for tungsten. Tungsten has been chosen for light bulbs. It works very well because tungsten actually has the highest melting point of all the metals that there are. Tungsten doesn't melt until over 3,400 degrees C. Okay, well, we have a little demonstration here to try and show this. I have here two cut-off light bulbs. Maybe if we can zoom in on these. Now, this is a rather tricky demonstration to show here. We've taken the tops off of these light bulbs, and at the moment there's still some gas in here. We're going to remove the gas with the aid of a vacuum pump. So first of all, let's just take the air out of here. Very good. Okay, and now, please. And now I'm going to switch on the light bulbs and just gradually turn them up. If we can have the lights down. And into the one with the green balloon, I'm going to let some air. And into the one with the white balloon, I'm going to let a gas called argon. Now let's see what happens. So the gases are going in. Let's turn up the voltage. And the one with the air has gone. It's blown. But the one with the argon is still alight. So even tungsten, with its very, very high melting point, it will still react with the oxygen. So we can't have any oxygen present in our light bulb. So when you buy a light bulb, there's no air in there. The gas is actually a different gas called argon, and argon is used because it's so unreactive it doesn't combine with the tungsten. Air would combine, and this is the chemical reaction that we have here, tungsten plus oxygen forming tungsten oxide. And actually, if we were able to look really closely at this light bulb, we'd see a very yellowy green colour of the tungsten oxide on the filament here where it's burnt away. Okay, well perhaps we ought to just find this in the periodic table. So the gas that we use instead of air is argon. And there it is up there. Very good. Well, you may have heard of some modern forms of these lamps. In fact, you may have heard of halogen lamps. So perhaps you can just point to the halogens, please. Oh, some of you are there. Yes, where are the halogens? Yes, very good. It's a whole family of elements. In fact, the halogens are fluorine, chlorine, bromine, and iodine. And we'll skip astatine down the bottom there. But so why do they use these? Well, these elements are very reactive. They combine with the tungsten, but then they can also decompose again on the very hot parts of the filament. And this can actually help prolong the life of the light bulb, or in fact enable us to turn up the light bulb so it glows even more brightly. In fact, so saying that these halogens were used in bulbs now, are used, but the early ones used to use iodine, so this is actually says tungsten iodine bulb, but later bromine came to be used instead, and so most of the halogen lamps that you buy now actually contain bromine. So these are some electrical light bulbs. One of the earliest electrical lamps, though, was actually discovered, or the basis of this was discovered as early as 1675. This is pretty amazing, really, considering that there was no batteries then, there was no way of producing a steady electric current, and yet the form of lighting that we use now and very often was discovered in 1675. I'll say what it was in a moment, but how was it discovered? Well, a French chap, a French astronomer named Jean Picard, who later became famous, of course, for being the pilot of the Starship Enterprise. But Jean Picard was walking home at night, on a very, very dark night, because, of course, there wasn't any lighting, no street lights in these days, in 1675, but he was walking home carrying his mercury barometer for some reason, okay? And he was sort of sloshing the mercury around, and there was some static electricity, and it actually lit up the gas in the top of his barometer. In the top of his barometer, what he had then was a few little atoms of mercury under very low pressures, and this was the earliest electrical discharge lamp. And this was later refined, and people generated their electricity using static electricity. Now we're going to try this. I'm going to generate some static electricity by rubbing a rod here and then moving it over some tubes that contain gases at very low pressures. And perhaps you can see, as I move this over, some red flashes. Well, this is the sort of thing that Jean Picard detected in 1675, just the tiny little traces here. And then this is actually now developed into the discharge lights that we see. And these at the moment contain colourless gases in glass tubes, but if we apply a voltage across them, they all light up with their characteristic colours. So we have helium at the top, neon, this bright sign, this is what we see in advertisements and so on, but argon, krypton, and xenon. So each of these gases gives a very different colour. Well, actually, the same principle is used to light our streets nowadays. We have a sodium lamp, and here I have a street light, which is actually a sodium discharge lamp. Notice the initial colour that we see here is actually due to some neon. But after a while, you'll see the colour change. We can begin to see some yellow come in here, okay? And this is due to the other element that's in this lamp, sodium. Now, sodium is actually a metal, but it melts very easily, and it can turn into a gas fairly easily as well. And this is what's gradually happening here. The neon is helping the sodium to vaporize, turn into a gas, and then this will give out a really brilliant light as well, and this is used to light up the streets. And this will be a rather nice yellow colour. But we need to leave that a little while before we can get the sodium to vaporize and see the full colour from it. But let's have a look at the lamp. Here we are. Here is our sodium street lamp, and if we look very carefully, we see that there are nodules. These are the metal lumps of sodium contained in this lamp. We have to wait for those to melt and then to vaporize, and then passing the electric current through this will excite these sodium atoms, and we'll get the yellow street lamp colour. So we'll keep half an eye on this. Well, this lamp was supplied by Philips, and this is the packet that it came in. It says here, for safety's sake, remove the lamp immediately if the altar bulb is broken. This lamp contains sodium. Well, this is what we've been talking about, the sodium. Contact with water can result in a violent reaction, stroke ignition. Avoid contact with water if the lamp breaks. Well, it's quite clear here, it really wants us to avoid water mixing with sodium. Well, I thought I'd show you why, okay? So remember, sodium is a metal. I have a lump of sodium here. And we're going to add this to the water in the tank. I'm just going to wash this. This is in alcohol, right? And we're going to drop this into the water at the bottom. Are you ready? And then get back. So you see now why you mustn't mix sodium and water together. Well, there's a chemical reaction going on there. Sodium reacts with the water, which we could also call hydrogen oxide, and it forms sodium hydroxide and hydrogen gas. Okay. Well, our lamp seems to be warming up rather nicely now, and there is indeed a very nice yellow colour beginning. We can see it coming from here. This is as the sodium metal in here vaporizes, and it's the atoms of sodium that have been excited by the electricity, and then we're converting the electrical energy into light energy. Actually, this bulb, when it's glowing properly, is really very, very bright indeed. And this is only a 35-watt bulb. Okay? This is the street lights that you see. Each one of these is just 35 watts. These are used because actually they're the most efficient means of converting electricity into light energy as far as our eye can see. Okay? There are, of course, new technologies being developed which may well be better than this in the future, but for the moment this is a very cheap source of light, for a lot of light for a little bit of energy. Okay, well, other things that contain sodium also give out this light. So in the spray can here I have some alcohol, and I've dissolved a little bit of sodium chloride in this. This is just common salt. Okay? And as it sprays through here, we get a brilliant yellow flame, exactly the same colour as the sodium street lamp. Well, different elements give slightly different colours. In fact, we could even identify which element we're looking at just by the colours that are given out if we analyse the flame very carefully. For instance, potassium chloride gives a very different colour. Nice lilac colour. Lithium gives a nice red. And copper, well, this one's just given a sort of greeny blue. And this one gives even more intense green. This is also copper. But you'll also recognise these colours, again, from bonfire night. Many fireworks contain these same elements to give them their colours. And here we have two, well, nominally indoor fireworks here. These are meant for theatrical purposes. We have two different ones here, and the green is due to copper, and the red one is actually due to the element strontium. But they're really rather beautiful. Perhaps we should find these elements then on our periodic table. If we can have sodium, first of all. We saw the sodium. Sodium has the symbol Na. Okay. We had copper, so that was in our fireworks and also in the sprays. That gave the green colour. And strontium, well, that was the colour used in the fireworks there. There's strontium here. So each of these gives a slightly different colour. Okay, so most of the methods that we've been using for generating light so far have actually involved combustion, using the oxygen from the air. But we can also have chemical reactions where there's no combustion, and, well, this is one that we have here. This involves mixing two chemicals, two liquids together. Okay? Now I have the two liquids in the flasks down the bottom here in the beakers, a solution of luminol and a solution of bleach. But when these two reagents mix together, they give out light. Now they're going to move up into this flask here. This flask, we've taken all the air out of here, and the air is pushing down on the beakers here, and that forces the liquids up into the top flask. But when the two liquids mix, then we see the light. So if we have the lights down, please. There we are. So this is the reaction of a chemical called luminol as it's being oxidized, and to cause the oxidation here we're actually using some bleach. So far we've seen different ways that we can make light, well, what can we do with the light once we've made it? Well, you've probably come across solar panels before. You've seen these. And I have a little solar panel here. So this is a way of converting light into electrical energy. And so just holding my solar panel in front of this light, it generates enough electricity to drive this motor. We're converting light energy into electricity. The solar panel uses the elements silicon. If you can find silicon, please. Very good. There's silicon right over there. Also uses gallium. If you can find gallium, there it is. Gallium's just underneath it, and arsenic. Arsenic's just over there. Okay, some of you are way off there, but never mind. Okay, what else can we do with this energy? Well, different things can also absorb this light energy, and I have here a very special thermometer. And one of the bulbs of my thermometer is painted black, and the other one is painted white. Now, we started off with these two levels here equal, but as I shine the light on this, you should be able to detect, and it takes a couple of seconds to get going, the black thermometer, the bulb on the black one, is going up faster than the bulb on the white side. Okay? And this is because the white is reflecting all of the colours here, whereas the black is absorbing them. It's absorbing this energy, and this energy is being converted into vibrations, and this is causing the liquid to expand, so the black one is going up faster than the white one. Well, we can also use this energy, this light energy, to bring about chemical reactions. And this is, of course, the basis of photography. Now, we have here a plate. We've made this with some jelly and some silver chloride. And at the moment, this is a nice white colour. Now, we're going to put a mask over this and shine some light on it. Okay. So, we have the white silver chloride. We're shining the light onto this now, and the light is causing a chemical reaction. The light breaks down the silver chloride and forms some silver particles. Now, these are a very different colour from the silver chloride. The silver chloride is white. The silver itself, well, silver is a metal and slightly metallic coloured. We should be able to see some of the silver being formed in this reaction. So we just need to give it a decent amount of time in order for it to react. So let's try this. Okay. And if we hold this up, we should be able to see here, there we are, silver chloride going to silver, and this reaction is brought about by the light energy. Okay, what else can we do with light? Well, I have over here a phosphorescent sheet. Now, at the moment it's being protected from the light with a cover. So, the light's off, please. Okay. Okay, we have the sheet here. Now, this is material that, when it's exposed to light, will glow in the dark. So if everyone with a laser pointer can please shine their light on this. Oh, very good. Some of them are nearly hitting it, yes. Very good. So, okay, and if we now have the lasers off, what do we notice? Absolutely nothing. Okay, let's try some yellow light. So here I have a yellow laser, and no one else in the audience, I don't think, has a yellow laser. And again, nothing happens. Let's try some green light. Ooh, still absolutely nothing. Well, finally, I'm going to try a blue laser. Now, for a while, this was the only blue laser in the country until our professor of organic chemistry decided that he had to get one as well. Okay, and this one is actually able to excite the phosphorescent material. Now, you might not be able to see this unless you're very close. I have another light source in my pocket. This gives out some UV light. This has even more energy, and this allows me to write on it. In fact, I have another UV lamp here that's even larger. UV. So this light has enough energy to cause the sheet to glow. Okay, thank you. Very good. So the phosphorescent chemical in there was absorbing the light energy, but it needed to have good, strong light to do this. Red light wasn't strong enough. It didn't have enough energy. Yellow light didn't have enough energy. Green light didn't have enough energy, but the blue did. Okay. Well, we've got one more sheet of this over here. Now, to use this one, I need a volunteer, please. Somebody close near the ends. In fact, right on the end here. Thank you very much. Very good. Now then, okay, we're going to take a picture of you. So, if you come over here for a moment, have the lights off, please. If you just stand here for the moment, we just need to take the screen off. Okay. Right. And just move this out of the way. Now, if you turn around, please, and face the screen. Hands up, hands up. That's it. Fingers out. On there. That's it. Lovely. You stay there. Legs apart. That's it. Legs apart. Very good. Right. Now close your eyes. Ready. Go. Now we're going to, that's it. You just stay still. And then move aside, please. Very good. Thank you very much. Okay, so again, the light managed to charge up the chemicals that we have there. But actually, as I say, it's only part of the light that has enough energy to get this phosphorescent material to glow. Okay, we need at least blue light and possibly even some UV light. Well, I don't know if you were convinced by my blue laser demonstration over there. I have one more demonstration to show you that might convince you that blue light has more energy. We've got some tubes containing two gases mixed up. We have the gases hydrogen and chlorine. Okay, can I have the lights down, please? So this is we have to be very careful here because the light, we hope, will set this reaction off. Now, Chris is just putting the tubes in front of the light source here. I say, inside the tube we have hydrogen gas and chlorine gas. Now this, as it is fine until we put some light energy into this. Okay? So with some light shining on this mixture, the light has enough energy to break apart the chlorine molecules into chlorine atoms, and this starts a rather vigorous reaction. Okay? So, are you ready? Okay, first of all, let's try some red light. No reaction. Some yellow. No reaction. Some green. No reaction. And some blue. Oh, there we are. Good. We've seen how light can be stored up by the phosphorescent material there and given out later. Well, sometimes species can absorb the light and convert one colour into another. So, for instance, we can take the UV light and convert this into visible light that we can see. So our eyes can't actually see UV light, but they can see other colours. And so here we have some tonic, just some normal tonic, but in UV, this glows really rather nicely. I have some fluorescein here. This glows rather nicely. I have some solutions here. These solutions contain organic polymers that were actually discovered in this laboratory. We have a red polymer, a greeny-yellow polymer, and a bluey polymer. In fact, they're not only excited with UV light, they're also excited using an electric current. We're going to see these in the future making up our televisions. We also have some minerals down here, and these minerals glow. And this one gives out a rather intense yellow light. The other thing that I have here is a fruit bowl. Well, here we are. You can see the fruit bowl glowing. This fruit bowl actually contains uranium. Okay? We'll come back to that in just a second. Just while I'm here, if we have the lights up, please, I'll show you this £20 note. You can see in the corner of this, just glowing there, 20. You can't see that in visible light, only under UV. We see the 20 showing there. Okay. Well, let's come back to my uranium fruit bowl. So uranium was one of the elements in the periodic table. And remember, this one is also radioactive. So perhaps my fruit bowl is radioactive. Well, let's see. I'll just have to bend over here so you can hear the Geiger counter. And yes, indeed, it is a radioactive fruit bowl. So we'll have to be careful what we do with that. Okay, so where it converts one form of light energy, the UV light, into a visible type is called fluorescence. And of course this will be familiar to you with the fluorescent tubes that you have at home. And I have a fluorescent tube here, just a normal fluorescent tube, sort of thing you've seen before. So this actually contains a small amount of mercury, the same sort of thing that Jean Picard discovered in 1675. This, with a little bit of electricity, gives out, well, it's actually mainly purpley UV light, but it can excite these phosphorescent coatings that we have on the lamps. Now, the lamp that I have on the top is rather a special one. On the end here, we have no coating at all, and you see the purpley colour. This is due to the mercury UV light. And the three colours that we have here, these are the phosphorescent coatings that are used to make up the white light. So all these three coatings are mixed up together, and we see these as the brilliant white in the fluorescent tube here. So this is how the fluorescent tube works. The elements for this, if we can just look on the last slide here, this shows some rather rare elements. We have cerium. If you can find cerium, oh dear, there we are, they're beginning to get there. Cerium, yes indeed, over there. Here's cerium. Europium, it's a rather rare element there. Europium. Gadolinium, very good, here. And terbium, and here's terbium. They also use a bit of yttrium, which is up here. Okay, so these are all the elements that are used in producing the light that we see in fluorescent tubes. If we look at the periodic table here, half of the elements, these are elements that we've discussed in this lecture, over half of the elements in the entire periodic table we've talked about in this lecture that are involved in producing light in various forms. Well, this just about brings me to the end of the lecture. So what have we learned? We've learned that we can convert different forms of energy into light energy, electrical energy and chemical energy. Well, we have one more example to show you, and this is our little bunny rabbit. It's made of something called nitrocellulose, okay, or gun cotton. He's very cute. So what do you think? Should we convert him into light? Yes, I think so. Okay, so here he goes. So now you see him. Woof. Now you don't. Just in case you missed the bang before, here we go. Hydrogen and oxygen making water. Thank you very much. Woof. Thank you.